Okay, so hi everybody. So today I'll be giving you some lecture on hardware, more specifically on superconducting quantum hardware. Um, why specifically superconducting? Because these days this is the most relevant application of this is the hardware for quantum computing. Um, and also it's relevant to the other courses that you're having here with the IBM and how to learn to use Qskit and everything lecture which you'll be having after this one. So in this lecture, basically, I want to try to give you an idea of the physics of superconducting qubits and also how we can perform some of the basic measurements, operations, let's say, of in a quantum computer, meaning quantum measurement, and also how you can use a pulse to create some operation of a qubit, like a single qubit gate and this kind of thing. So I'll start. Oh, yeah. I'll start with something with a little bit of technicality, just to give you an idea of the physics, and then I'll move on to show some simulations. Okay, so just as an introduction, so obviously superconducting qubits is not the only platform. There are various platforms, so which have their own specificities in how you encode quantum information. So you'll have, for example, trapped ions. In trapped ions, the idea is you store the quantum information in ions, right? In different orbitals of the ions. In diamond vacancies, basically nitrogen vacancies, you will be storing the quantum information in electrons, electron spin, which is basically trapped in one of these vacancies. In quantum optics, you store your quantum information in photons. So you'll be creating photons. You just do operation on photons. You encode it in polarizations or different ways, and that's how you can you do your quantum computation. Then you have even cold atoms. You trap atoms, you cool them down to very low temperature, and so here you'll be encoding the information in atoms. And in superconducting circuits, basically you'll be encoding quantum information in circuits, electronic circuits, or to be precise, in collective oscillations of charges in electronic circuits. So if I ask you, what is like one of the big differences that you can see between electronic circuits and the other four platforms that I gave you, what would be one of the big differences that comes to mind? Which is more fundamental?
The other four.
Oh, the other four are more fundamental. Yes, in some sense. Basically, in the sense that they're much smaller. They're individual systems, right? So they're individual quantum systems, as opposed to quantum circuits, which are huge objects because they're electronic circuits made of aluminum, made of millions or billions of particles, right? So we'll be really looking at macroscopic quantum degrees of freedom, whereas in the other ones, we're not looking at that. And that is one of the perks of superconducting qubits, is that they're so big, you can build them, you can manufacture them. That is one of the big advantages of using this to do quantum computing.
More scalable.
For now, it's clearly superconducting qubits. It's the only one that has been able to go to that many kind of qubits with these kind of this kind of success.
I think another superconducting qubits makes more sense because it is more in relevance with the classical computers compared to other four. The circuits level,
yeah.
Gate level, everything is having some sort of relevance with classical computers. That's why I guess superconducting.
Oh, yeah, it's still very different. But you're right; it has the same size as so you can. It's similar in that sense because the chips are almost same size as like transistor kind of thing. That's true. Okay, so now I want to basically define and give you an idea of what are these quantum degrees of freedom that we're dealing with quantum circuits. So here I just want to go through a typical derivation of how we quantize this kind of objects, just to give you an idea. So So you know that we in quantum mechanics we use Hamiltonians to describe the physics of what we look at. So for that, I'm going to have a look. So Hamiltonians is the energy of the system. So first we'll start classically. The energy, you'll have two different energies in an LC circuit. So the LC circuit is like the fundamental quantum circuit, right? It's the harmonic oscillator. And this is going to be kind of the basic recipient for quantum informations. So so you'll have two types of energies here, right? We'll have capacitive energy, which is going to be 1/2 of CV squared, right? And the charge here in a capacitor would be equal to CV. So I can rewrite my energy as being charge squared over 2C, kind of a typical expression. We also have inductive energy, which is going to be E equals 1/2 of L, the current squared. Now, also for inductive energy and for inductor, we generally write it in terms of flux. Flux equals the inductor times the current. So I can rewrite this energy as being phi equals over 2L. Now, see, these circuits are generally 2D. Okay, there's 2D circuits. So if I ask you what is phi, what comes to your mind when I talk about phi in this kind of classical circuits? Flux.
The magnetic field lines.
Right. If it's flux of magnetic field, right? Generally, that's how we see it. So, but the thing is, that requires a coil. That requires some kind of a flux going through a 3D loop, right? But that's not the case because our circuits are basically like 2D circuits. We basically print them on 2D silicon chips for most of them, for at least quantum computers that we deal with today. So phi cannot just be B dot ds in this context. Okay, this is not applicable to 2D circuits. Instead, what you have to do is define a generalized flux. Generalized flux. And that generalized flux is going to be given by the integral of voltage around some element. So here is my voltage, right? It's ground here. The integral from this from minus infinity to t. Minus infinity because we're supposing that there was no voltage at time equals 0. So you define it this way. Okay. And you can just check that this makes sense because when I differentiate my d by d phi by dt, I'll get v of t. Okay. So this is basically equivalent to the usual relation that you know, v equals L di by dt. Okay. So there we are. This is how we get the energy of such a circuits to be q squared over 2L plus phi squared, sorry, over 2C is 2L. Exactly. So basically we have our energy now, which is basically going to become our Hamiltonian. Now in quantum mechanics, what we do is we have to quantize. This is still a classical circuit, so we quantize. By quantization, we mean that one, we make Q an operator, and phi flux also an operator, and we impose quantization. We impose commutation relations. Okay. So the commutation relation is Q phi. Right. So this is exactly analogous to what you have in classical mechanics, where you have xp, exactly, xp equals IH bar. It's just exactly the same kind of system because they're both a harmonic oscillator, mechanical harmonic oscillator, or a circuit, LC circuit. They're both harmonic oscillators. So physically, we deal with them exactly the same way. Just the variables have different names. This is, yeah, exactly. I'm just doing first quantization for a harmonic oscillator. The only thing is the variables are different. Instead of X and P, you will be getting Q and phi. Now, just for the following part, I need to define the notation that we'll be going to use, and it will be a dimensionless notation. So we defined dimensionless variables. So which are going to be the number of electron pairs. So the thing is, I told you I'm not going to go in detail about that because that would be too much. But of course, we have superconducting circuits. So the basic thing about superconductors is that all electrons are paired into Cooper pairs. So we don't talk about individual pair, we talk about Cooper pairs. So you just have to suppose, just have to assume that the element of charge is not E, but 2E. So then the number of Cooper pairs is going to be your charge divided by 2E. So the charge of one single Cooper pair. Okay, that will be our variable. And the other one is the reduced flux. Reduced generalized flux, but for short, we won't just be saying generalized all the time. So it's going to be divided by a constant. It's just a constant called the flux quantum. So, and I can rewrite my Hamiltonian. So, right. So, okay, when I said quantize, also my energy is going to H, the Hamiltonian. H is going to be 1/2 of 2En squared plus 1/2L phi 0 phi squared. Okay, so we obtain Hamiltonian, which looks like this: EC n squared plus constant, inductive constant, over 2 times the flux. This is the same Hamiltonian. I'm just rewriting things. Charge. So this EC is what I've defined as a charging energy. EC equals E squared over 2C. And EL, I've just rewritten. Okay. Just defining some notation. That's why I'm going through a little bit of algebra. So this is basically a number of pairs. Let's say times the charging energy. So that'd be your energy due to capacitive energy. Okay. It's the same as my Q squared over 2C. And flux is basically the amount of current going through my inductor times the constant. Okay, so that'd be my inductive energy. That's that. So last point I want to make, and finally we'll be arriving to the concept of quantas, is then we diagonalize. So that's also important because I need that, yeah, diagonalize. So what we do in quantum mechanics is define operators. Basically, just a constant to EL to 1/4 A plus A dagger plus A, and charge, or sorry, it's not charge anymore. We're using N, number of pairs, exactly. This is minus I EL over 32 EC. 32 EC 1/4 A minus A dagger. Okay. So if you define these operators A and A dagger in this way, first thing is you can show that A dagger have these commutation relation. A dagger equals 1. Okay. Now you can use that. Now if you just plug this in your Hamiltonian, plus EL over 2 phi squared. Okay, you plug this in this Hamiltonian, you'll see that you diagonalize your Hamiltonian over A dagger A plus 1/2. Okay. So that's a very important expression. That's basically the Hamiltonian of a harmonic oscillator, the most basic object of a quantum circuit in some sense. And so this expression, basically this commutation relation and this Hamiltonian, and you can show that if your eigenstates are labeled by integers 0, 1, 2, etc., then these ladder operators A and A dagger are going to allow you to go from one to the other. So one is going to be basically just A dagger over 1. Sorry, of 0, yes, exactly. More generally, what you see is that A over n is going to be square root of n plus 1. So these ladder operators allow you to move from one state to the other. Okay.
There's a fundamental limit, right? Like we cannot go below
you cannot go below 0. Exactly. 0 is kind of the limit. You can also prove that just by playing around with those relations, but I'm not going to do that.
This harmonic oscillator is the same.
Exactly. It's a harmonic oscillator. Exactly. Yeah. And you can also do A dagger n will be square root of n plus 1. Oh, sorry, here it had to be n minus 1 because this destroys an excitation. And this one is going to create an excitation. Okay. And then the energy of these states of an energy n is just going to be, you can also draw. Exactly. It's going to be n plus 1/2. That just comes from the fact that A dagger A is just the operator for the number of charges. Okay. So that if I sandwich this operator A dagger A over one of my states, let's say my state n is like one of them, you just get n, the number of excitations. Okay. So these are basically my excitations and basically the nature of the quantum information in these quantum circuits, that basically these quanta. So it's not exact, they're not exactly photons, we'll see that a bit later. But okay, so these states in the harmonic oscillator, this is the potential of your harmonic oscillator. You will see, so this is the energy. There's going to be, you will see that you had equally spaced energy levels. That would be 0, 1, 2, 3, and they're all separated by the same energy h bar omega. Okay. So these states basically they correspond to single quantum in the system, which are basically generally called in the context of circuits plasmons. But nobody really uses them because they're so much analogous to photons that people just call them photons. Okay. And in this lecture also, I'll also just be using photons. Because at the end of the day, they're just electromagnetic degrees of freedom. There's still a fundamental difference that here we have a circuit and we have circuit charges that create magnetic fields and electric fields. So they're photons, but created with charges. Whereas when we deal with quantum optics, it's a pure electromagnetism. That's the main difference with actual electromagnetism, but it's still the same nature of degrees of freedom. Any question about the basic quantum mechanics? That's basically mostly what I just wanted to reintroduce so that we're clear with the notation and the vocabulary for this lecture.